Hello, students. Our last topic was refraction of the light, and this is like a continuation for the refraction of the light. And we will discuss here how the refraction takes place in the optical instruments called as lenses. This is optical device, and how can we use this refraction effectively. The lenses are these kind of transparent objects, and one side needs to be spherical. Some are thinner from the center and thick at the edges, and some are thick at the center and thin at the edges. But at least one side should be spherical. There are different kind of lenses we have. So here we will discuss only the first one, uh, biconvex, that is thick at the center and both sides are spherical. And here this is the first one is biconvex, and this is called as biconcave. The others are used for some specialized purposes, and we will not discuss actually those, but the basic principle that you will understand, so then you can actually extend the understanding to the others also. The biconvex lens, its property is when we send a beam of light, a parallel beam of light on it, the whole light actually converges at one place. This is the reason this is also called as a converging lens. And the application of this lens is actually, the natural application is our eye. So our eye has a biconvex lens inside our eyes, and that makes actually the images. And the second, you can see the camera. So camera works exactly like the eye, and we get an upside down image on the surface of the camera. In inside the eye, the image is actually made upside up with like the brain system, and in camera it doesn't matter actually whether the picture is upside down or not, so it doesn't matter. The concave lens, the biconcave lens, is something when you send a parallel beam of light on it, it diverges, and it diverges in a way that it seems to come from a single point. And the we can see further objects which are larger in size, but with this kind of lens we can see them smaller. So let's discuss the biconvex lens in more detail. So we can consider a parallel beam of light that is sent on the surface of a biconvex lens, and then after passing through it, it actually converges at a single point and then diverges again. So this point where the whole light converges is called the principal focus. And the center of the lens, geometrical center of the lens, is called the optical center. And if we draw a line passing through optical center and the principal focus, this is called as the principal axis. The distance between optical center and the principal focus is called the focal length, and that's really very important. So we can define the focal length on both sides because it's transparent. So you can see here f is defined on both sides, and double of the f is 2f. So keeping these things in mind, we need to construct the images from the biconvex lens, and we need to know how the rays actually behave, different rays. We need at least two rays to construct the images. We will study here three, and any two you can use. A ray of light that is parallel to the principal axis must always pass through the focus. So from anywhere it passes, whenever it's parallel to the principal axis, it passes through the focus. Any ray that comes from the focus become parallel. So both are actually the same. One is parallel that passes through the focus, and if coming from the focus, because it's transparent, so it comes from either side. So there is no difference. And the ray of light that is passing through the optical center, then the it shows no change in path. So anywhere the ray of light, this shows no change of path. Now we make the images at different locations. For example, the object is placed beyond 2f. So usually the objects are shown with an up arrow, and we take the rays of light coming from the top of the object. So one ray of light that is coming from top of the object, which is parallel to the principal axis, it will pass through the focus. And another we can consider a ray of light that passes through the optical center, shows no change in path. So the intersection of these two rays is a place where the image is formed. So we can say the head of the image is at this location. So we can say that this image is formed upside down. So the properties of this image is, number one, it's real. What does it mean by real? So real is an image that can be obtained on a screen. So for example, where the image is, we place something, for example, a cardboard or a wall or anything. So you will get the image over there. And the real image is always formed with the intersection of the real rays. So this image can be seen on a screen, that is called real. Any image that we can see inside the instrument but not on any screen, that is called a virtual image. So if you remember the plane mirrors, we can only see our image inside the plane mirrors, not anywhere else. So that was a virtual image. So this is, we can see on a screen, we can obtain on a screen, that's real image. And this is upside down, we call it inverted. And this is smaller in size, we call it diminished. And this is of course between f and 2f. So this could be used when the object is away. So the lens make an upside down smaller image. So our eye is an example, and in the artificial devices, the camera is an example. What about if we place the object at 2f? So we take again the rays of light, one that comes from the parallel to the principal axis from the top of the object, and then it passes through the focus. The other that passes through the optical center, it shows no change, and now you can see there is no change in the size of the object, and it's actually made at the same position, but it's real, it's upside down. So we say it's real, it's inverted, it's same size, and it's at the same position. All right, so what about when the object is made more closer and it's between f and 2f? So we take the same two rays again, and now we can see a larger image could be seen. So this act like a magnifier or a projector. So projector uses these kind of lenses to make the more larger images of small images and show us on a screen. So it's real, it's inverted, it's enlarged, and it's beyond 2f. And the application is the projector. What about if we place the object at the focus? So if we draw these two rays of line, it means these two become parallel, and the parallel lines never meet each other. So if we extend them back even, they don't meet. It means they are not able to make any image, because image is only formed if these two rays combine together at some place. So no image is formed when the object is placed at focus. What about if we bring the object more closer to the lens? That means inside the focus. These two rays of light shows that they will not make any intersection because they are diverging. But if we extend them backward, they do intersect, and they actually make an image which can only be seen inside the lens. So we cannot see it on a screen because it's not made by the intersection of the real rays. We just extend them back and we can see a larger image. So we have to see inside the lens to see this image, not on a screen. So these kind of images are called the virtual. It's not, it's of the same orientation. It means we call it upright. It's enlarged. And the application, we cannot define actually the distance of it because this is a virtual distance, not a real distance. So this orientation of the lens can be used as a magnifying glass, or we call it a simple microscope. So in for a magnifying glass, what we do is we bring the magnifying glass closer to the object, and the object is the map. So when it's closer to the object, it shows us a larger image, but inside the lens only, not anywhere else. So the magnifying glass actually makes a virtual image, and it's of the same orientation, so upright. The biconcave lens, a parallel beam of light diverges, and it diverges in such a way that the rays of light seems to be coming from the center, from the one point, and that is called the focal point, or the principal focus. This is an example of that a larger object could be seen as smaller. The ray diagrams, any ray that is parallel to the principal axis diverges in such a way that it seems to be coming from the focus. And any ray that is coming towards the focus actually become parallel. And any ray that goes through the optical center is undeflected. We place the object usually away, and this is an object. A ray of light that is parallel to the principal axis diverges in such a way that it seems to be coming from the focus. The another one that goes to the principal axis. So you can see an intersection of a real ray and an imaginary virtual ray. So it doesn't make actually a real image, but a virtual image that can only be seen inside the lens, and it's smaller in size. So wherever actually you place an object in front of the concave lens, you get a similar image every time, that is virtual, upright, and smaller in size. Let's consider a, a lens of focal length f. So this is the focal length. So from here till here, and we call the distance of object from the center of the lens, that is DO, and the distance of the image from the center of the lens is DI. Then these three quantities, focal length, distance of object, distance of image, they are related to each other with an equation that is called the lens equation. In order to use this equation, you need to be careful. Um, F is positive for a convex lens and negative for a concave lens. DO is always positive, and DI for a real image it's positive, and for a virtual image it's negative. So whenever you use this equation can be used for both biconcave and biconvex, but you need to be careful regarding F and DI. And we define another quantity that is called the magnification, and magnification is what is the ratio between di and do, and this can also be defined in another way, that the heights of the object. And because it's both define the same thing, it means we can write them equal to each other. So the ratio of distances of the object and images is the same for their heights, and this is called the magnification. The two application for the convex lenses, we see a smaller object as a larger object as I described, and this is called a simple microscope. So a single convex lens could be used as a simple microscope when we put the object inside the focus. If the object is not inside the focus, then we cannot get actually a virtual image inside the lens. So this is basically a magnifying glass. But if we use two convex lens in such a way, then we can actually make a compound microscope, and it makes actually the magnification 2 times. O is the object. The first magnification is done with a lens which is called as objective. It's closer to the object, and then it makes a real inverted image closer to the eyepiece, but this is inside the focus of the eyepiece. So you can see this makes again a magnification because this is inside the focal length of the eyepiece. If the focal length for the objective is FO, and the focal length for the eyepiece is FE, then it makes actually the magnification 2 times. In case of system of lenses, the magnification is not actually added, but it's multiplied. So it's very useful because the factors are multiplied. So we get a more better magnification if we use two lenses in such an orientation. Objective has a smaller and the eyepiece has a larger focal length. So this is FE actually. Okay, that's end of the refraction, the application of the refraction as the lenses.